Hi everybody, in this video we are going to cover section 4 of chapter 4 where we will evaluate logarithms and talk about the change of base theorem. First we're going to talk about the common log, which is a very common logarithm. Then we're going to talk about the natural logarithm, which is the most natural logarithm in a number system, and we'll show why that is the case. We'll talk about a few applications throughout, and we will conclude with the change of base theorem, because as you know, it's all about the base, no treble. Here we have the common log, and what is the common logarithm? It's nothing more than the log where the base is equal to 10. Of course, since the domain of any logarithm is all positive values of x on the real line, x will always be greater than equal to 0. Now note that in this particular case, the common logarithm of 10, well, is basically equal to 10 raised, is that power that you need to raise 10 to get, well, yeah, 10, which would be 1. The common logarithm of 100 is that power that you need to raise the base to get 100, which in this case would be 2, because 10 squared is 100. And similarly, the common log of 1,000 is 3. Also notice, and this applies for any logarithm with a positive base, if the argument is a number between 0 and 1, the logarithm will always be negative. And if the argument is greater than 1, then the logarithm will always be positive. And we will have an example to show you that that is indeed the case. Okay, so what you want to do here for our first example is to use a calculator to find each value and then to express your answer to 4 decimal places. Well, the first one, we don't even need to use a calculator. Remember, this is the log of 10,000, so we want to find that value, that value of y, or that value that we need to raise 10 to get 10,000. And of course, if I raise 10 to the 4th power, I will get 10,000, so this will be equal to 4. Now, if you actually have to write this in 4 decimal places, then that would be 4.0000. There's my 4 decimal places. However, in your homework, when you have something like this, all they want is the exact answer, which in this case would just simply be 4. Now for this problem, we want to find the common log of 150, and here we actually need to use a calculator. So you can either use your TI-84 series calculator, or your TI-30, or your Casio, or the calculator in Windows, and here I'm going to use this online calculator because this is the one that best emulates a TI-84 series calculator. So we want to find the log of 150, and how will we do that? Well, the common log is expressed by using this key right here, log. So I'm going to press on that. I'm going to type in 150, and then I don't want to do that. I actually want to close the parenthesis and then hit equal, and I will get this number. Now, since I want the answer to be accurate to with 4 decimal places, I'm first going to look at the first 5 decimal places. And if I do, I will have that this is equal to 2.17609. Now notice that the 5th decimal place is a number greater than 5, so that means I want to round up, and I want to round the 4th decimal place up by 1 value, which would bring that to a 1. And so this would approximate 2.1761, and this is what I would want to put into MML. All right, now let's take a look at log of 0.00648. So here's my calculator. I'm going to clear. I'm going to hit log, and that's going to be 0.00648. Close the parenthesis. Don't really have to in this particular case, but it's probably good practice. And that will give me 2.18842, the 5th decimal place, of course, being 2. So I'm going to go ahead and write that down. You don't really need to write it down. You just kind of need to note what that is and act accordingly. So here we have, and I'm sorry, that was -2. Since it is actually less than 1, our log is going to be a negative value, 2.18842. Let me make sure I get that right. Yep, it is. Okay. Now notice that this is less than 5, so we do not need to round up, and so this will approximate to negative 2.18884. Okay, so that's the first type of things that you'll have to do relative to common logs. The next things that you will encounter, or the next type of problems that you will encounter, are applications, and the first one being the application of the pH of a solution. So the pH of a solution is defined as minus the common log of H3O plus. And what the heck is this? Well, this is the hydronium ion concentration in moles per liter. And what is moles? Well, basically, we can say that, well, I can sort of show you with an example. If you actually looked at a carbon atom, it would have the it would have the atomic weight of 12 AGU, and I forgot what AGU stands for. I think it's like atomic mass, or I actually would have AMU or something like that. Well, basically, 1 mole is enough carbon atoms. It's enough carbon atoms so that you would actually have 12 grams of carbon. For another example is oxygen, which actually has an atomic mass of, well, 15.99, but it rounds up to 16. If you had 1 mole of oxygen, that would map to 16 grams, or I'm sorry, 15.99 grams. So that's pretty much what a mole is. What we just need to know here is that the pH is really a measure of the acidity or alkalinity of a solution. So the pH of pure water, pure water has a pH of 7, and we tend to call this neutral. If the pH is greater than 7, then the solution is alkaline. If the pH is less than 7, then that solution is said to be acidic. So things like orange juice or your favorite glass of wine are typically acidic solutions, or vinegar or something like that. So what kind of problems will you be encountered? Well, one like this. You're going to use the definition of pH to find the pH of a solution whose concentration is 5.3 times 10 to the negative 3 moles per liter. So how do we compute that? Well, once again, the pH is equal to the common log of the concentration of H3O plus in terms of moles per liter. So in this particular case, we are going to have that the pH is going to be equal to negative times the common log of 5.3 times 10 to the negative 3. Okay, so that's what we need to compute. So we're going to go to our handy dandy calculator. We're going to clear, and then I don't think I can do minus yet. I can do minus sign, common log, there it is, and then I'm going to do 5.3 times, and then I'm going to use this function right here, 10 to the negative 3 power. Close parenthesis for that, close parenthesis for the log, and my answer is going to be 2.27 and everything else. Now, when we express pHs, we are only interested in expressing it to the 10th unit. So here, I'm going to write this down to the 100th unit, which will be 2.27. So I will have here, the approximate value would be 2.27. Once again, we want to round to the 10th unit when we're dealing with pHs, and that will bring it down up to 2.3, and that is our answer. Now for the next one, we want to find the hydronium ion concentration with the pH is 7.5. So we know what pH is, we need to figure out what this is. So we can do a little manipulation here, and we have that negative pH is equal to the common log of H3O plus. We can now look at our equivalent equation, which would be 10 to the negative pH is going to be equal to H3, the concentration of the hydronium ion, which is this. All right, well, I forgot the H here. And of course, 10 to the negative pH is going to be 10 to the negative 7.5, and that's what we need to compute. So let's go ahead and do that. Okay, let's go ahead and clear. We can use the 10 function here, and then type in negative 7.5, close our parenthesis, and we get, oh my goodness, what is that? Well, check this out. We have 1, 2, 3, 4, 5, 6, 7, 8. So if your calculator could express this in scientific notation, I'll say, wait, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. Since there's 7 zeros, your calculator could express this as 3.1677, I'm sorry, 3.16227 times 10 to the negative 8th. Basically, 10 to the negative 8th kind of implies that there would be 7 zeros in front of the decimal place. Okay, but if you wanted to, you could also write this as 0.1234567316227. They are indeed equivalent. Now, typically we will want this to be accurate to the 4th decimal place, since we are actually looking for a concentration and not a pH. So notice my 5th decimal place is 7. So this would approximate to 3.1623 times 10 to the negative 8th. And our units would be moles per liter. Okay, the other type of problems that you will see in this particular section have to do with the intensity of sound. And it turns out that the loudness of sound is usually in terms of decibels, which in general is nothing more than a ratio. But when we're dealing with sound, we tend to have an accepted fixed reference value, which is 10 to the negative 12th, which we call I sub 0. And this is in units of watts per square meter. So it's not a power density, because a power density would be watts per cubic volume, or per volume. So this is basically just watts per square meter. Not exactly sure what we call that. We call that an intensity, or basically it's just power per unit area. Anyways, this is called the threshold sound intensity, and is considered to be the lowest detectable volume heard by the human ear. Now, it doesn't turn out that this does change slightly as with respect to audio frequency, but nonetheless, this is considered to be the accepted amount. And then I sub O is given by the intensity of the given sound. And then decibels, the sound intensity in terms of decibels, is 10 log that particular ratio. So one of the problems that you're going to see in your homework is this. Find the decibel rating of a sound with intensity of 1,000 times I sub 0. So fortunately, this is already expressed in terms of the threshold sound intensity. And all we need to do is basically substitute this for I. So we're going to have D is equal to 10 times the common log, or sometimes we'll say log base 10, 1,000 times I sub 0, and of course that's going to be divided by I sub 0. Conveniently, these cancel. We will have 10 times the common log of the common log of 1,000. Now, a lot of you can immediately see that this should be 3. If you can't, go ahead, punch into your calculator. You'll get 3. So you will have 10 times 3, which would be equal to 30. And that would be your answer, 30 decibels. Oh, and by the way, decibels is basically 1/10 of a bell, because deci stands for 1/10. And the unit bells is named after a particular famous person. I think many of you know. It's Alexander Graham Bell. Okay, and this brings us to our discussion of the natural logarithm. And remember that number e that we talked about just in our previous lectures? Well, it's going to rear its ugly head once again. The expression natural log is nothing more than the log base e. It represents the exponent which our magical number e, Euler's number, must be raised to in order to obtain e to the x. Okay, so the log of e to the x is, of course, x. Okay, and once again, x is always greater than 0, and this is the primary reason why this is called the natural log. Take a look at this. This is the function, the reciprocal function. It's nothing more than f of x is equal to 1 over x. And it turns out that the natural log of x will always be equal to the area under this particular curve. Here we have x being equal to 6, and the shaded area here is the area underneath the curve of f of x from 1 to 6. And that area would be equal to the natural log of x. It turned out that if x is equal to 1/2, say right here, call that x0. And then this area, the area from 1 to negative 1/2, would also be equal to the natural log of x sub 0, or 1/2 in this case. However, we would consider this a negative area. And this is why why this is called the natural log, because it actually occurs naturally in our number system. Every other logarithm is also an area under a curve that looks like this. However, that curve will always be scaled up or down by the actual base of the logarithm. Or actually, that curve will always be scaled up or down by the log base e of whatever your new base might be. And you kind of get an appreciation for that when we talk about the change of base theorem. Now remember how we talked about the log of e is that number where the area under the curve 1 over x from 0 to that number is equal to 1. Well, here is the log of base e, or here is e right here. And if you evaluate the natural log at e, you would get 1, and the area under this curve would be equal to 1. Okay, so what kind of things are we going to want to do with this? Well, once again, we are going to want to evaluate various values, the natural log for various values. Now, in many cases, we will need to use a computer. In this case, we definitely don't, because this is the natural log of e raised to the 73.3 power. And the answer to this is going to be, what power do we need to raise e to get this value? Well, obviously that would be 73.3. Typically, when you are given a problem like this in this particular form, you're going to want the exact answer, and this would be it. If they wanted your answer to 4 decimal places, you just need to add 3 more zeros, and then these would be your 4 decimal places. Now, for the rest of these problems, you would actually need to use a calculator. So here we want to find the natural log of 56. And how would we do that? We go to our Mr. Calculator here. Now, on many of your calculators, you will find a key that says ln, and we pronounce that Lin, like the girl Lin. This one, in this particular calculator, I have to highlight the log. It appears. Well, first I need to clear. Now I can highlight the log. It appears. Click on that. Type in 56. Close the bracket. And I get 0.02535. So I can write that down. This is approximately equal to 4.0253. The fifth decimal is 5. Since the fifth decimal is 5 or greater, I'm going to round up. So this will approximate to 4.0254. The next one is ln of 0.00864. And of course, we'll do that the exact same way. We'll come to our calculator, first clear, hit ln, and then we will have 0.000864, close our parenthesis, hit equal, and that will be our response. Negative 7.0539. We want to go ahead and include the other 3 because that's the 5th decimal place. However, since that is less than 5, we have no rounding that we have to deal with. So writing this down to the 5th decimal place, which you really don't have to do. You can do that. You can do that in your head if you would like. Negative 7.05393. Notice that this is less than 5, so no rounding is required. So we have negative 7.0539 would be our answer. Okay, once again, you will have some application problems to deal with, and here is one of them. This problem was probably developed by a naturalist and a statistician. So here we have the number of species given by a sample, or a number of species in a particular sample is given by S evaluated, and which is going to be equal to A times the natural log of the rate of the value 1 plus n over A. So this will always be greater than 1, which means that your answer will always be positive. Now here, n is the number of individuals in the sample. So this is all the stat part, and then A is the constant that indicates the diversity of the species in the area. That's probably the naturalist part. And we're going to assume that A is 0.77, and we need to figure out what S sub n is. Well, first thing I want to just throw out here is that S sub n will always be an integer. Okay? And so basically what we need to do is just evaluate this formula for the case where a is equal to 0.77 and for n is equal to 50. And that will be 0.77 times the natural log of 1 plus 50 divided by 0.77. And if you evaluate that with your calculator, you should get an approximate answer of 3.2. Okay, once again, we're only interested in integers, and since the decimal place, since the 10th value is less than 5, this rounds to 3. Okay, for the next one, we just replace 50 with 250. You guys can go ahead and do that. And if you do, you should get an answer for S sub n. I'm sorry, S sub 250, I guess I should say, of 4.4. And of course, that will round to 4. And this brings us to the change of base theorem. Now notice in my calculator, well, in this particular calculator, I can compute common logs, I can compute natural logs, and in this one, not in every calculator, you can actually compute log base 2. But what if I wanted to compute the log of another base? Well, you can't do that directly with the calculator. You need to apply the change of base theorem. And this is what it says. For any possible positive real numbers a, b, x, a, and b, where a is not equal to 1 and b is not equal to 1, the following holds true. The log base a of x can always be written as the log base b of x divided by the log base b of the old base a. And for your viewing knowledge, I am going to go ahead and prove this. Yes, just for you. So how would we do this? Well, how about if we just set y equal to the log of base a, or log base a of x? Okay, now what can we do with this? Well, probably the only thing that I can think of doing with this is maybe we can write this in the equivalent exponential form. And if we did, we would have a to the y is equal to x. Okay, is there anything else we can do? Well, we're actually looking for the log base b, and if I actually applied the log base, and if I actually took the log base b, it would have log base b x over here. So hey, let's go ahead and do that. In that case, then we're going to have log of base b evaluated at a to the y is going to be equal to log base b of x. So we have this, so that's kind of helpful. And now we have basically the log of something raised to a certain power. So we can use our power property and rewrite this as y times the log base b of a. And of course that is still equal to the log base b of x. All right, well, now I can go ahead, and so I have this, which is what I'm looking for, which is here, and I have this, so I can actually divide both. I can divide both sides by log base b of a, and I will have that y is equal to log base b of x divided by log base b of a. All right, check this out. Y is equal to log base a of x, so I can replace y with that. Log base a of x, and that is equal to log base b of x divided by log base b of a, and I am finished. And that is basically how you prove that theorem. Of course, we don't care about proving theorems, so yeah, I'm sorry, I just wasted 2 minutes of your time. We want to know how to use this sucker, so let's go ahead and do that. Here we have the log base 2 of 16. All right, now if you guys remember correctly, log base 2 is 16 is going to be equal to that power, I'll call it y, that we must raise 2 to get 16. And that would be 4, because 2 to the 4th power is equal to 16. All right, now what would you get if we actually computed the log, the common log of 2, divided by, no, 16, sorry, the common log of 16, divided by the common log of 2. Or what would you get if you took the natural log of 16 and divided that by the natural log of 2? Well, let's go ahead and find out. Better before, or not after, but before, or I'm going to look kind of silly, right? Okay, so we're going to have here the common log of 2. 16, my apologies. 16, and we are going to divide that by the common log of 2. And what do we get? We get 4. Hallelujah, just what we were getting, hoping. Okay, let's do this with the natural log. Natural log of 16 divided by the natural log of 2. And you guessed it, we get 4. And then finally, well, since it's here, the natural, no, don't want to do that, clear. The log base 2 of 16, if you wanted to, we could then divide that by the log base 2 of 2, but that'd be kind of silly, is 4. So that also gives you a certain degree of confidence that I actually have some clue as to what I'm talking about. Okay, well, what about the log base 4 of 20? Well, you can write this as the common log of 20 divided by the common log of 4, or the natural log of 20 divided by the natural log of 4. It doesn't particularly matter. And you will get something to the effect of 2.61096. Since the 5th decimal place is greater than 5, this will round up, and the 9 will become basically 10. So we'll carry the 1 over here. We'll have a 0, and that will give us an approximate value of 2.6110. That's supposed to be a 2. There we go. Okay, well, what about this sucker? We have the log of the square root of 5, log base square root of 5 times 9. Well, since the square root of 5 is a number greater than 1, it can be a base. So how would we do this? Well, let's just play with natural logs this time. This will be the natural log of 0.9 divided by the natural log of the square root of 5. Square root of 5. Okay, now if you wanted to, you don't have to, and I actually don't advise it, you could rewrite that as the natural log of 0.9 divided by 1/2 the natural log of 5. But that's not really necessary. You can just go ahead and do it like this. And if you did, you would get an answer of negative 0.13092. Since the 5th place is less than 5, this would round up to negative 0.1309. And that is all for that example. I have one more set of examples, and these are basically designed to help you with your homework, because you actually see a lot of these. And the first one is the natural log of 98 divided by 13. Now, using what you know about the quotient property of a logarithm, we could write that as the natural log of 98 minus the natural log of 13. I really don't prefer to do that. I would prefer to go ahead and just do this directly. Specifically, I would just basically click natural log, and type in 98 divided by 13. And that will give me 2.00201, which will round to 2.0200. So we would have, well, what about this? Well, once again, you can compute it directly just like this, but personally, I would prefer to compute it as the common log of the product. Why? Because I think there's fewer keystrokes. I think, in my opinion, it's just a little bit easier to do. So I would first multiply out the 296 times 12. That's taking advantage of the product property of logarithms, and then take the common logarithm of it. And if doing so, I would have 296. First clear log 296 times 12. That gives me 3.55047, which would round to 3.5505. And once again, since this is greater than 5, we will round this up to 3.5505. Okay. And then finally, you can do this directly, or you can take advantage of the quotient property of logarithms and write this as log of 84 divided by 17, which is how I would do it. And if you did, you would get negative 0.1309, with the 5th decimal being 2. Of course, since that's less than 5, there's no rounding, or the rounded version, we don't need to round up, and that will give us negative 0.1309. And that is all that I have for this particular section. If you have any questions, please feel free to contact me. This is Bob Oil, signing off.